What's up, geeks, and welcome to the channel. We already know that every character is represented using a sequence of ones and zeros in binary code, and that is done using the corresponding ASCII code of that character or letter. So the letters A and B, for example, will be represented as you can see in front of you. Consequently, if the text we want to represent in binary was something like that, and was only made of these two letters, based on what we just said, the binary representation of this text is this. But if we know that all we need are the letters A and B, then why not represent this text like that? Isn't this a much more efficient and compact way to represent our text? Well, that's what David Huffman also said. The Huffman Coding Algorithm is a lossless data compressing technique used to reduce the size of a given input without losing any of its details. It is generally useful on data with frequently occurring characters just like the one we had. Okay, let's see how this algorithm works. Suppose we have a string made of the 21 characters you see in front of you. Each character occupies 8 bits, thus usually a total of 8 times 21 equals 168 bits are required to represent this string. Now, to represent the same string using Huffman, you need to start by calculating the frequency of each character in the given string. So in our example, the A occurs 8 times, the B 7 times, the C 4 times, and the D 2 times. These characters should now be sorted in ascending order, based on their corresponding frequencies as you can see in front of you. Okay, until now it should be straightforward, but here comes the tricky part. We are now going to use the character frequency pairs we just sorted to construct a tree, a binary tree to be more precise, and these pairs will be the leaf nodes of this tree. So to construct the tree, we start by picking the two lowest frequency leaf nodes from the list we have. The sum of their frequencies will be the frequency of their parent node. The created node is then added to the same list. Remember, every two elements we pick from this list must have the two smallest frequencies. One way to ensure that, while implementing, is to make use of a priority queue. This process is then repeated on all the nodes inside the list, which contains now 3 nodes, until all that is left is one single node. The root node of our tree, which also stores the total number of characters contained inside the original text we are trying to encode. Now, every left edge of the tree is assigned a value of 0, and every right edge of the tree is assigned a value of 1. And the code corresponding to each character can be deduced using these values by reading them from the root all the way down to the character's leaf node. So, the A will have a code of 0, the B a code of 1, 1, the character C a code of 1, 0, 1, and the character D a code of 1, 0, 0. Now, instead of representing each character with 8 bits, we can represent it using the Huffman codes we just generated. Okay, I know most of you may be thinking that this cannot be decoded uniquely, that there must be multiple ways to decode this series of ones and zeros. Well, let's try to decode it together. 3 out of the 4 codes we have start with a 1. So the first starting 0 must be the character A, right? So is the second and the third, all the way till we reach a 1. Now we have a bunch of 1s, and since we have no code to represent a single 1, these must be all Bs. Let's note them down. Next, we have a 1, 0. But since there is no code for that, we must consider the 1 next to them as well, which makes a C. The 1, 1 that follows them cannot be a B, as there is no code to represent the remaining 1, 0 preceding it. See, you get where I'm going. Whatever you do, whatever you try, there is only one way to decode this string. This uniqueness is ensured because we applied what we call the prefix rule. And this rule states that a code associated with a character should not be present in the prefix of any other code, and the tree we created ensures this property is maintained. So the codes you see in front of you are not valid Huffman codes, as they violate the prefix rule. The 1 is the prefix of the 1, 0, for example. However, none of the codes we generated using the tree is a prefix for one another. Hence, they are valid Huffman codes. Okay, let's go ahead now and try to implement both the encode and decode methods, and after doing that, I guarantee that things will become clearer and easier to understand. The Huffman algorithm is based on the fact that we are creating a tree, and to create trees we need nodes. So the first class we are going to implement is the node class. This class, on top of having the usual left and right child references, will have the frequency, which in our case is the data we need to store inside it. We also mentioned that while creating new nodes, the frequency of these nodes will be the sum of its left and right child's frequencies. And that is exactly what we are doing in the constructor you see in front of you, all while assigning its children to actually build the tree. Additionally, these nodes are to be stored inside a priority queue, as we previously mentioned. And for it to function, the priority queue has to compare the elements stored inside it. And this can only be made possible if this node class implements the comparable interface and overrides the compare_to method. The comparison here should be based on the frequency, because while building our tree a few moments ago, we were picking the two elements with the smallest frequency. Now, the difference between the Huffman tree nodes and normal nodes is that its leaf nodes store an additional piece of data on top of the frequency, and it is the actual character. Remember, the character is only stored inside leaf nodes, but the node we just created doesn't account for these cases. Therefore, what we can do is create another class, the leaf class, which extends the node class and add to it the character attribute. Okay, onto the Huffman class. Inside this class, we need to keep track of the original provided text to encode, of the frequencies of each character inside this text, of the tree we built using these frequencies represented by its root node, and of the Huffman codes we generated with the help of this tree. Okay, when a new instance of the Huffman class is created using the constructor, the first thing we need to do is retrieve the frequency of each character. This was done with the help of the fill_char frequencies map helper method. Here all we need to do is loop over the characters of the input text, and for each character either create a new entry for it in the map, or increment the count value of the frequency stored inside it. Now that our frequencies are calculated, let's go ahead and try to encode this text by generating its corresponding Huffman codes. To do that, the very first thing we need is to create a priority queue, as we mentioned several times. Then we have to add to this queue all the character frequency pairs stored inside the map we just populated inside the constructor. Do not forget that these pairs are all leaf nodes, as they also store the character, and hence should be added using the constructor of the leaf class. After doing that, we have to keep polling the two lowest frequency elements from the queue and use them to link and generate new nodes for our tree until all that is left is one single node, the root node of this tree. The last step is actually generating the codes, and this was done recursively using the generate Huffman codes method. You see, every code will start with an empty string, and for every character we have, if we go left inside the tree in attempt to reach it, we append to this code a 0, and if we go right, we append to it a 1. We will keep doing this until we reach a leaf node, only then the Huffman code will be complete, and will be added to the map of codes we instantiated at the level of the class. With this, our codes are now generated. Finally, to retrieve the encoded text, I invoked the getEncodedText method, which will simply loop over the characters of the given text, and replace each character with its corresponding code after fetching it from the codes map we just populated. Now, to decode the encoded text, we need to loop over every digit or character of this text, and for each digit, we need to traverse the tree we built by going left if it is a 0 or right if it is a 1, until we hit a leaf node, which means a valid Huffman code. So, when we have a hit, we retrieve the character corresponding to this leaf node and append it to the string builder we created, which at the end should consist of the original text we started with. Do not forget that after every match, we should reset our tree to the root to be able to decode the next digit. Let's go ahead now and see our implementation in action. To do that, I created an instance of the Huffman class inside the main method and provided it with the same text we used at the beginning of the video. I also invoked the encode and decode methods. However, because their output isn't kind of readable, I created a very simple helper method that will print the codes for us, because that is basically what we care about the most when implementing this algorithm. As you can see, the printed codes are similar to what we got at the beginning of the video and are exactly as expected. Finally, if you've watched our trees visualized upload, you may be familiar with the tree view class I used to draw the tree implementations we covered using JavaFX. That's the same class I am making use of here. And what you see is the output of the Huffman tree we just generated for the same input text. So, that's it for this video. I hope it was helpful. Thank you guys for watching, take care, and I will see you in the next one.